Hi, I recently got a new scope. My old Rigel I sold and I bought this new DHO-804, well known probably. I updated it a bit, I hacked him a bit to a higher bandwidth model, but this video is basically about what you can do with the scope and also what you can improve on it. Some things that are nice on this scope are actually that it has a remote control interface. So with a network, you can just access it. I'm Dutch, sorry. And from this IP address, you get live data, so you can actually enable channels, disable channels. And you see if you disable it, you get this nice pop-up. And I find this annoying because what I want to do, my scope is not close by. I want to change the vertical settings. And it can be done like this, but it's a bit tedious because if I want to do the same here, I have to click twice and I have to change it like this. What I prefer more is a direct interface. So the first thing that I did is I wrote a small script and I'll start it up. I call it DHO-REMOte, and that's that resembles DHO-REMOte. I think that was written for the previous Rigel, the 1054 DH set or something like that. Well, whatever. You probably know it. So let's start the program. And it connects to the scope. And now I can control all those things here, like the vertical settings. Can put it on and off, etc., etc. They are not well updated, but so I have now only channel 1 enabled, and I can all do the things that I want. And one of the things that I also wanted to do is have a Fourier transform of the picture and display it right away on my screen here instead of on the scope. The scope does have a decent FFT. I can actually show that. That's this one. Please go away, thank you. Let's do the start at 0. By the way, it's 1 kilohertz signal on the screen. So let's say 100 kilohertz. Stop and the start 0 start end, yeah. 0 to 100. 20 dB per division. And this is how it looks like. What I don't like about this plot right away is that it has a linear graph, especially for repetitive signals. I want to have a log scale because that better displays the amplitude versus frequency. And there is not a lot you can do here. You can set an offset. Well, basically you can also do that like this. You can just grab it over in this. And it is reasonably fast, so it is nice for eyeballing and say, yeah, there are harmonics here. And you can actually see there are harmonics. We expect that, right? Because this is a 25% square wave signal. I expect a fundamental. I expect a first, third, fourth, etc. Every harmonic should be there. And that amplitude is displayed here. So I made my own version of that. I just grabbed the data from the scope with the Python script. And print some statistics here, and this is what I get. And the first one, the top one is the same as here, except that this one goes from 0 to 18 megahertz. 18 megahertz is, by the way, the half of the sample rate, because you do not want, you don't have any information above half the sample rate. So this is the same plot as here, but you can also plot it in a logarithmic scale, and it clearly shows that there is a nice, decent slope of 20 dB per decade for all the harmonics. 1 over n, that's the amplitude of the harmonic, and n being the harmonic number. And it shows that at 1 kilohertz there is a signal with this amplitude, and it falls down. I also put some noise in here, so you can do all kind of fancy things, and at the end there is also a display of the time domain. I just find it handy. You can do anything. This is just NumPy or Python plot. But then I realized after some discussion in the EV blog forum that, well, basically you can also make a Bode plot of it. Bode. It's a Dutch guy, so it's not Bode. And I'm also Dutch, so I know. So I enabled the second channel, and okay, the amplitude needs to go up a bit. I said up, not down. But you first need to know what I have. So I will show that the setup. Okay, this is the setup that I have. What do you need for a Bode plot? Well, normally you need a sine wave signal generator that you apply to the DUT. This is my DUT. But I instead put a square wave on there, and there is an idea behind that. So this is my my Unity pulse generator. It generates 1 kilohertz at the moment. 800 millivolt peak, 25% duty cycle. Comes out there, burp. It goes to the scope directly, so channel 1 is basically the signal generator, and the blue cable goes there. And that is the DUT. The DUT is a LC, it's a 22 nanofarad capacitor and a coil in parallel, and that resonates at 110 kilohertz. And I can see that, and I can show that later on. And the output of the resonant tanks goes to the other channel, and that is terminated by 50 ohm. So basically that is my setup, and that is what you should remember. Okay, back to the desktop. So now I have the two signals on the screen, and they look very similar because, yeah, it just passes through the signal, except there is some filtering going on. And you can barely see that if I plot the FFT of the second channel. That's this one. Make some room. So this is the first channel, this is the second channel, and you can actually see that around 100 kilohertz there is a bump here in the frequency transfer at the input, channel 1, and there is a bump down at the second channel. And that's basically because the 50 ohm termination is then connected to the channel 250 ohm is connected to the generator. Or is no longer connected because it is filtering. Okay, so these two signals contain all the information that you need for the Bode plot, because FFT contains both amplitude and phase for every harmonic. So what I did is close this one. I created a simple script that basically measures all the harmonics, and when the harmonic is big enough, I plot it on the screen together with the phase, and that's what you normally call a Bode plot. So here you can see that I started up with a signal of, well, read the scope, 1 kilohertz. So the first point is actually here, and this is some bleeding of the FFT, but that doesn't matter. So 1 kilohertz to, well, let's say 3 decades you can clearly see. So although the amplitude goes down, the relative amplitude and the relative phase can still be measured up to 3 decades. And after that, the signal becomes a bit too small, so I sort of quit at 1 megahertz. So at this point I say, well, that's not good enough. So that's nice, but what you can do, for instance, is change the time base. You can make it faster and plot it again. You can see how fast that goes. If you would scan this with a sine wave controlled generator, it would take a lot more time. So it is still 1 kilohertz, but well, you can see that it doesn't really matter much because the time base is not directly used. What is used is the sample depth, and the scope is set to 1 mega samples. So the FFT is also using the raw data, the 1 mega samples, and the sample rate. So the sample rate is currently 625 mega samples. So it will go all the way to 300 megas, and that's what you see here. So basically the frequency, the higher frequency goes a bit further, but that's not used for this particular measurement. So zooming in this deep doesn't really help, but zooming out you can also do the other direction. And note that the sample rate now goes down to 12.5 mega samples. So I plot again. Move it out of the way for comparison. So now you see exactly the same, but you see the noise is a bit less, but it is still all with 1 kilowatt, with 1 kilowatts sampling. So for 1 kilowatts, 10, 100, and 1 megahertz. That's about the range. But what some users asked is, can the dynamic range be extended? And actually, I think that could be done, and I know it can be done because I implemented it. And that's capturing twice. So instead of doing this once, I do it 2 times with different frequencies. And first, I'll show you what happens if you change the frequency. So this is all done with 1 kilowatt. And now I put my generator on 100 hertz. Okay, so you can see on the scope here 100 hertz. Time base, yeah. Oh, starts to scroll. So I'll put it like this. So now I'm going to do the analysis on 100 hertz. My plot. And you can see that I can still see it here, but now it starts off with 100 hertz. So 1, 2, 3. So I now have the lower part of the frequency, and that's normally what a Bode plot. If you use a scanned frequency, a sine wave, then it becomes very slow because everything needs to settle for every frequency point, and that's not needed if you use a square wave signal. So this is 100 hertz. I can also use 10 hertz, but 10 hertz. And you can see it is now 10 hertz, and I do it again. And now probably it will not fit on the screen. There you are. So it starts at 10 hertz, but the harmonics at 110 kilohertz, where it starts to resonate, yeah, they're too weak because the frequency is too low. In theory, you can still see it here, but I don't want to do that. I want to just say, well, it needs to have a certain signal to noise ratio. So what I do instead, I will close all those plots because they become a bit too much. So I can also capture into 2 stages. So what I call is capture low. Okay, that's now done. Now I change the generator to, well, what shall we do? 10 kilohertz. Then, where's the K? There is the K. Okay, I should leave this screen untouched so you can't see the waves, but now I do capture high. So this is the second capture. And basically that gives me 2 sets of information. And with some software, I just merge the 2 sets into one. And you can see it here from the frequency spectrum. Oh, that's actually not nice. It's a demo effect. Let's try it again. Let's capture at 100 hertz. Capture low, yes. So I've now kept it to low part, and then I go to 10 kilohertz. This is just playing around, so the software is not really completely debugged, but the concept seems to work. Yeah, it does work. So now you can see that from 100 hertz onwards, you see the the harmonics go down, and here at 10 kilohertz a new harmonic comes in. And at 10 kilohertz and 20 kilohertz and 30 and 40, etc., both measurement point will be used. And here you see actually that yeah, there are some phase errors. So I still need to work on this part to make it correct, but yeah, that's work in progress. So I think at the end it should be possible to make a Bode plot well in two goes from 5 decades in frequency. And I also tried the same with the crystal. So I have also tried to measure the crystal. That also works. So it is a bit playing around, but I think for those not having the 914S of Rigel, it is this might be an option to get your Bode plot working. Another thing that I added here is a simple save thing. So as soon as I play save, the data of this channel 1 is automatically saved to channel 1. This is just the user interface, and it gives me the things that I want. You can also do that from the scope, but I think it is like storage. Yeah, you have to say save wave, data source, memory. And where do I specify? Oh yeah, you can do it like this as well. But here, if you save it, you can also do it to a Samba drive. But let's save it like this to a local. Save it, and then it saves it to to a Rigel DSO bin. I don't want to have a bin because I cannot use that. I want to have a comma separated file. And then save it. And then I have to pull it from the scope because I want to post-process it. That's not very handy. So instead I just have the file here, and that's let's show how it looks like. Channel1.csv. It's just a long list of time points separated by a comma and then the amplitude. So yeah, it's nice for post-processing, but do note that this raw data, that's the size of the scope, the memory depth. So these are 1 mega word count minus line. So there's 1 million lines of code. So if you just put it in the spreadsheet, you have 1 million rows. It doesn't work. So yeah, it's nice to save it as an ASCII comma separated file, but yeah, you probably want to limit that to 10K instead of, or the alternative is to dump the information on the screen, because the screen itself has a much lower resolution than what you capture. And you can see that from here. So this bar on the left and on the right, it's grayed out because you don't see that, but you can move this screen to the left and to the right because the amount of data that is captured is much larger than the amount of data that is on the screen. This is just for 10K, but if you do 1K and you run it, and this scope is nice because it can actually capture 25 megasamples because I have two channels enabled, and that allows for very nice FFT small bins. So you can be very selective in your harmonics, and you can it's nice. And here, if I zoom in, you can actually see what I'm testing. So the input is the generator, and the output, that is the scope, the channel 2. And that is what the Bode plot also shows.